Hello, it's Dr. Harris with another edition of MAT225 video chats. This time we're going to talk about section 8.2 in our text, arc length and surface area revolution. So the question we start off with is, if I took a piece of a curve, take y equals f of x between x equals a and x equals b, and I were able to pick up the ends of that curve and stretch it out and put it up against some sort of measuring device, how long would it be? And so we were thinking about straightening out a curve and measuring its length. And so we're going to talk about how we can first approximate that and how the approximation might lead us to realize what the formula that we need to use is. So if you go to your book on page 473 and look at figures 1 and 2, you'll see what process is being suggested here, and that is that we take the curve and we replace it with line segments. So we take partition points along the curve and then we connect them with line segments. And we can find the length of the line segments using the distance formula. And then what we do is we do a neat little substitution involving the mean value theorem, and we'll see we'll get our formula for the length of one of the segments, and then our approximation will be the sum of the lengths of those segments, and then we'll take a limit as the number of segments goes off to infinity. So before we get deep into that, though, let's remind ourselves about the mean value theorem. It says that if a function is continuous on a closed interval and differentiable everywhere except possibly at the endpoints of that interval, then you can find a number in the interior of the interval, that's a less than c less than b over here, satisfying f of b minus f of a equals f prime of c times the quantity b minus a. You might divide both sides of this equation by b minus a, and you'll see that this side would be the slope of the tangent line, and the remaining f of b minus f of a over b minus a would be the slope of the secant line joining those 2 points. And if you need a refresher on the mean value theorem, you can look at pages 230 and 231 of your text. But we're going to use that in our simplification below. So if we just take a single segment joining 2 points on our curve, xi, f of xi, and xi plus 1, f of xi plus 1, this is simply just the distance formula, square root of the sum of the squares of the differences between the x coordinates and the y coordinates. But it's here that we apply our mean value theorem. We're assuming that our function is continuous and differentiable appropriately. And so we'll treat this as b, this as a, and so we can replace f of b minus f of a with f prime of c times b minus a, where c lives between a and b. And now you notice that xi plus 1 minus xi is just delta x in disguise. So I'm going to replace this with delta x and this with delta x. And if we've got a product being squared, we can write that as the product of the squares. And now delta x squared is a common factor. So I can extract that from underneath the radical. I get delta x times the square root of 1 plus f prime of c sub I squared. And so that's the length of one of my segments. And so if I take all n segments that I've got from my partition and add them up, that will give me an approximation of the arc length. And then we'll get the exact answer by taking the limit as n goes to infinity. And that will give me an integral from the left endpoint to the right endpoint of the square root of 1 plus the square of the derivative of the function. So if we can evaluate this integral, that will give me the length of the arc of the function between a and b. Let's work a few examples. Our first one, let's find the length of y equals 4/3, x plus 1 to the 3 halves over the interval from 0 to 3. So we want to set up our integral, so we'll calculate the derivative. We get 2 times the square root of x plus 1. When we square that, we get 4 times the quantity x plus 1. And so 1 plus f of x f prime of x squared is going to be 1 plus 4 times the quantity x plus 1, which when I expand and collect gives me the square root of 4x plus 5. We're integrating between 0 and 3. This is a pretty straightforward substitution problem. We'll let u equal 4x plus 5, then du is 4 dx. I change the variable, so I'm changing the limits as well. When x goes from 0 to 3, u is going from 5 to 17. And so I get 1/4 the integral from 5 to 17 of u to the 1/2. That's easily anti-differentiated. I get 1/6 u to the 3/2. I evaluated 17. I evaluated 5. There's my exact answer. If you'd like a decimal approximation to 3 places, then it's just a shade under 10. Our second example uses some slick algebra. It's a little bit of an artificial type of problem, but it turns out that things work nicely with just a little bit of algebraic insight. So our function is y equals 1/4 x squared minus 1/2 times the natural log of x. We're going over the interval from 1 to 2e. And before we get too deep into this, let's remind ourselves that a minus b quantity squared looks like this, and a plus b quantity squared looks like that. So the only difference is I go from a minus 2ab to a plus 2ab. That's going to have some bearing in this problem. So, excuse me, y prime is going to be 1/2 x minus 1 over 2x. And so when I square that, this is going to be of the form a minus b quantity squared. I get a squared minus 2ab plus b squared. But if you look carefully at 2ab, that simplifies to negative 1/2. So I get 1/4 x squared minus 1/2 plus 1 over 4x squared. When I add 1 to that, what happens is I get 1 minus 1/2 for my constant, so that's going to become plus 1/2. So I've swapped off the minus 1/2 for a plus 1/2, but that's still going to be 2 times 1/2 x times 1 over 2x. And so this is a perfect square as well. It's 1/2 x plus 1 over 2x squared. So the minus here has gotten changed to a plus. So our arc length then is going to be the integral from 1 to 2e of the square root of a perfect square. And so we get just this sum here to integrate. We can do both of those pieces. This is now a plus. So it almost matches our original function up here. The minus has been changed to a plus. And then I evaluate between 1 and 2e. I get e squared plus 1/2 of 2e for putting 2e in, and I get 1/4 plus 0 to subtract away by plugging 1 in. And then, just to simplify a tiny bit, natural log of 2e is natural log of 2 plus natural log of e. Natural log of e is 1, and so I get a 1/2 minus a 1/4 here. And so my answer, the exact answer is e squared plus 1/2 natural log of 2 plus 1/4, which is just a little bit under 8. But most functions, we can't actually evaluate the integral of the square root of 1 plus f prime squared. And so we're going to often use something like Simpson's rule to answer a question like this. So even something that looks relatively simple, like y equals 1/2 x to the 4th, we're not going to be able to anti-differentiate the square root of 1 plus f prime squared. F prime is 2x cubed. When we square that, we get 4x to the 6th. And so my arc length literally is the integral from 0 to 2 of the square root of 1 plus 4x to the 6th. I don't know an antiderivative for this, so I'm going to go back and rely on Simpson's rule. I've suggested we use n equals 8. Delta x is 1/4. I plug this function into my calculator. This is what I expect to have to evaluate with delta x equal to 1/4. Delta x over 3 is out in front. And I'll trust you to go to your calculator, enter this function, see that these are the numbers that you get. And so I get about 8.8 as my approximate length. So, read over the parts of the section that I suggest, and look at these examples and see if you have any questions. The other topic that gets addressed in this section is surface area revolution, where we're going to be revolving a curve around an axis again, but this time we don't want the volume of the solid that is resulting. We want to maybe treat this as just a surface, and we want to find out what the surface area is, the lateral surface area. So we're going to go back and think about that the lateral surface area of a cylinder is 2 pi RH. That's going to factor into our formula below. Again, I'll encourage you to look at a figure in the text. Look at figure 9 on page 476. The actual surface area that we're going to be approximating is that of what our authors call a slanted band, which we could think of as part of a truncated cone. If we lopped off the top of a cone, we would get that shape. And what we're going to do is we're going to approximate the surface area of that truncated cone, that slanted band, with the surface area of a cylinder. And so, again, we're going to pick C sub I to be in between my two endpoints. And so f of C sub I is going to be the radius of my approximating cylinder, and the height of that cylinder is going to be the length of the segment. And so it's going to be 1 plus f prime of Ci squared, delta x again as the height. And so we're approximating that slanted band with a cylinder, and so I get 2 pi times the radius times the height. If I add all those up, that will give me an approximation of the lateral surface area of the resulting figure. When we take the limit as n goes to infinity, we get 2 pi integral from a to b f of x times the square root of 1 plus f prime squared dx. One quick example to show how we can solve these problems. Again, our capacity is pretty limited. We're often going to have to go with a Simpson's rule type of solution. But here's one that we can work. Y equals x cubed over 1 to 3. We revolve that around the x-axis. I didn't state that on the page here, but we're revolving around the x-axis. Y prime equals 3x squared, so we can square that. And so our integral becomes 2 pi f of x square root of 1 plus f prime squared dx. We're fortunate in this case that we can use a u substitution. And so we'll let u be what's under the radical. Here's du. We change our limits again. We go from 10 to 730. And so we get 2 pi over 36, integral from 10 to 730, square root of u. Again, I'm missing a du here. We anti-differentiate, and we evaluate. And we get a rather large number this time. Other problems might involve, I guess, use trig substitution. Integration by parts is possible. And as I mentioned, Simpson's rule is always a live option.